Okay, in this class, we are continuing our discussion on the quantum mechanical treatment of the one-dimensional harmonic oscillator. Okay, we have reached part 4 of this lecture series. Okay, so far what we have learned, I am going to summarize it. Okay, we have a particle here, and that particle is moving in the plus x and minus x direction periodically. Okay, so that is a vibration motion, and this is a simple harmonic motion. And we have set up the Schrodinger wave equation for this system. The Schrodinger wave equation is minus h square divided by 8 pi square m d square by dx square plus 2 pi square m nu square x square into psi is equal to E psi. This is in the form of h cap psi is equal to E psi. This is a Hamiltonian. The first one is kinetic energy term and the second one is the potential energy term. Here m is the mass of the particle, nu is the frequency of oscillation, x is the displacement from the main position. Okay, E is the total energy of the system. And a modified Schrodinger equation has the form d square psi by dy square plus alpha by beta minus y square into psi equals 0. Here alpha is 8 pi square me by h square, beta is 4 pi square m nu by h, and y is equal to root of beta into x. Okay, and the general solution for this equation, that is psi is equal to f of y exponential minus y square by 2. Okay, and here f of y is a term which was introduced here without knowing the expression itself, and the expression for f of y was obtained as a solution for the Hermite differential equation. Okay, that is what we learned in the last class, that Hermite differential equation is d square f by dy square minus 2y into df by dy plus alpha by beta minus 1 into f is equal to 0. And the solution of this Hermite differential equation is a Hermite polynomial, and the Hermite polynomial is h and y. That is, for f of y, we get h and y as the solution, and the expression for h and y is minus 1 raised to n exponential y square d raised to n by dy raised to n exponential minus y square. Okay, and with this information, now we can get the expression for psi, because psi is equal to already we wrote here psi is equal to f of y into exponential minus y square by 2. So in place of f of y, we can give the Hermite polynomial. Okay, so that is h and y exponential minus y square by 2, that is multiplied by n, which is a normalization factor for this function. Okay, and here n is equal to 0, 1, 2, 3, etc. Okay, this is what we have learned so far. And in this lecture, what I am going to do is I am going to give the exact expressions for psi. For that, I have to evaluate psi and y, h and y for different values of n, and also I have to get the normalization factor. Then I can make the expression for n psi, that is equal to n h and y exponential minus y square by 2. Okay. Now, let us first go for the normalization factor. So the normalization can be done, normalization of the wave function. Okay, so normalization can be done by minus infinity to plus infinity. Okay, psi xi n y square. This is this psi depends upon the quantum number n, so we can write like psi n, and also it is in terms of y, so we can write psi n y. Okay, psi n y. Let me write it better, otherwise you will be confused. Psi n y. Okay, so this one. So this is psi n y. Okay, psi n y square dx. Okay, psi n y square dx, that is equal to 1. Okay, that is a normalization condition. Okay, and that is integral minus infinity to plus infinity n h n y exponential minus y square divided by 2 the whole square dy. So sorry, it is not dx here, we have to give dy because y is a variable here. Okay, dy is equal to 1. Okay, so if we are solving this one, if we are solving this is a lengthy solution, and if we are working on this integral, we can evaluate n. Okay, and I am giving the final expression for n from here. N is equal to root of beta divided by 2 raised to n, 2 raised to n factorial root pi raised to half. Okay, raised to half. Okay, so n, this is a normalization factor, root beta divided by 2 raised to n factorial root pi raised to half. Okay, and you may be wondering how this root beta appeared here in this expression, because you cannot see any root beta here. Actually, you know that y is equal to root beta into x. Okay, from there only the root beta is appearing here. Okay, so interested people can refer some textbooks and go for this lengthier differential solution for n. Okay, and n is equal to root beta divided by 2 raised to n factorial root pi the whole raised to half. And now we have an expression for n. Okay, and from this one we can find out the value, the normalization factor for different values of small n, because we know that n can have the values 0, 1, 2, 3, etc. So for each value of small n, we will get a normalization factor. Okay, so let us find out for n is equal to 0. Okay, for n is equal to 0, we have the normalization factor, that is n0, which is equal to root beta divided by 2 raised to 0, 0 factorial root pi the whole raised to half. That is equal to root beta divided by 2 raised to 0, 0 factorial, that is equal to 1. So we have root beta divided by root pi raised to half, that is equal to root beta by root pi is beta by pi the whole raised to half, right? So beta by pi the whole raised to half raised to half, that is equal to beta by pi raised to 1 by 4. Beta by pi raised to 1 divided by 4. Okay, so that is n0, and like that we can find out n1, that is for n is equal to 1, we have another normalization factor, that is n1, which is root beta divided by 2 raised to 1, 1 factorial root pi the whole raised to half, that is equal to root beta divided by 2 raised to 1 is 2, 1 factorial is 1, that is 2. Okay, 2 into root pi the whole raised to half. Okay, and therefore we can write it like 1 divided by root 2, 1 divided by root 2, because 2 raised to half is root 2, 1 divided by root 2 into beta by pi raised to 1 by 4, beta divided by pi raised to 1 divided by 4. So that is the expression for n1. And like that, for n is equal to 2, we have n2, that is equal to root beta divided by 2 raised to 2, 2 factorial root pi the whole raised to half, that is equal to root beta divided by 2 raised to 2, that is 4, into 2 factorial. 2 factorial is 2, that is 4 into 2, that is equal to 8, right? So root beta divided by 8 into root pi the whole raised to half, that is equal to 1 divided by root 8 into beta by pi raised to 1 divided by 4. Okay, so we have different values, different normalization factors n0, n1, n2, etc. corresponding to the different quantum numbers n is equal to 0, 1, 2, 3, etc. Okay. And now what we have to do is we have to find out the expression for h and y for different values of n, because we already have found out the expression for n, normalization factor for different values of n. Like that, now we are going to the next term, that is the Hermite polynomial h and y, and we have to find out the different values of this h and y with respect to different values of uh, uh, the quantum number n. Okay. So let me write the expression for h and y once again. I will do it in another color. That is h n y is equal to minus 1 raised to half, right? Minus 1 raised to minus 1 raised to n. Sorry. Minus 1 raised to n exponential y square. Exponential y square d raised to n by dy raised to n, d raised to n by dy raised to n exponential minus y square, exponential minus y square. Okay, so minus 1 raised to n exponential y square d raised to n by dy raised to n exponential y square is h and y, and we have to find out h and y for different values of n. And for n is equal to 0, for n is equal to 0, now we can calculate the value for h and y. Okay, then h and y can be written like h0y, right? h0y is equal to minus 1 raised to 0 exponential y square d raised to 0 by dy raised to 0 of exponential minus y square. Okay, so that is equal to minus 1 raised to 0, that is equal to 1 into exponential y square into d raised to 0 of dy raised to 0 for exponential minus y square, that is equal to exponential minus y square. Okay, so these two terms, they will be cancelled because you can bring this in the denominator, so this one and this one will be cancelled and we will get 1 instead of that. So the entire value is 1. Okay, so this is equal to 1. So h0y is equal to 1. h0y is equal to 1. And now we are going for the next one, that is n is equal to 1. For n is equal to 1, we have to estimate h1y, that is minus 1 raised to 1 exponential y square d raised to 1 by dy raised to 1, means d by dy of exponential minus y square. Okay, that we have to evaluate. So that is equal to minus 1 into exponential y square into d by dy of exponential y square, that is exponential minus y square into derivative of minus y square, that is equal to minus 2y. Okay, minus 2y. So we get minus into minus, that is equal to plus. So we get 2y here already. Okay, 2y, and then exponential y square and exponential minus y square, they will be cancelled. So what is remaining is 2y. Okay, and therefore h1y is equal to 2y, or in in terms of x, we can write like that is equal to 2 into what is y? Y is root beta into x, so we can write like a root beta 2 root beta into x. Okay, that is h1y, 2 root beta into x. And now we can calculate for n is equal to 2. N is equal to 2, and you can do this calculation yourself. But anyway, I am going to do it here. But I suggest you to pause this video for a while and do the calculation yourself, and then you can play this video to see whether your calculation is correct or not. So for n is equal to 2, we have h2y, right? h2y 2y is equal to minus 1 raised to 2 exponential y square, then d square by dy square of exponential minus y square, okay? So that is equal to minus 1 square, that is equal to plus 1, right? Plus 1 exponential y square into d by dy of first derivative of this one, that is exponential minus y square into minus 2y, okay? minus 2y, okay? So what we have here is that is equal to 1 is already here, so that is 1 into exponential y square into d by dy of this quantity, okay? So there is a constant here, that is minus 2, so I can bring this minus 2 here, okay? So minus 2 into dy of exponential minus y square into y, okay? So there is a, let me write it here, t by dy of exponential minus y square into y, exponential minus y square into y, okay? So now this is a product of two functions, so we have to take the derivative of that, so that is equal to minus 2 exponential y square, okay, into dy of this one, that is first function is exponential minus y square into derivative of the second, that is equal to 1 plus second function y into derivative of the first function, that is exponential minus y square into minus 2y, okay? So we have to write like minus 2 into exponential y square. We have to multiply all these with the exponential y square. So what we will get when we are multiplying these terms with the exponential y square? So exponential y square and exponential minus y square, they will be cancelled. So what is remaining here is 1 plus y into exponential minus y square. So exponential y square and exponential minus y square, that will be cancelled. So what is remaining here is minus 2y into y, that is minus 2y square, minus 2y square, okay? That is equal to minus 2 into minus 2y square, that is equal to 4y square, and then minus 2 into plus 1, that is equal to minus 2. So what I get is 4y square minus 2, okay? 4y square minus 2. So I can write like y square is equal to beta x square, right? So I can write it like, because y is equal to root beta into x, y is equal to root beta into x, therefore y square is equal to beta x square. So let me write like 4 y square is beta x square minus 2, okay? 4 beta x square minus 2. So this is h2y, okay? So now we have the expression for h0y, h1y, h1y, h2y, okay? And like that we have for n0, n1 and n2, okay? And now what we have to find out, we already have the in the expression for psi, this is the expression for psi, and here we already have n for different values of n, and we already have h and y for different values of n, and the last term is exponential minus y square by 2. Okay, so how can we write exponential minus y square by 2? Exponential minus y square by 2 is nothing but, okay, we will write exponential y square minus y square by 2 with another exponential minus y square divided by 2. Okay, that is equal to exponential y square is beta x square, so we can write like minus beta x square, okay, divided by 2. Okay, so now we have uh, everything to write the psi psi expressions for different values of n. Okay, so let me make the different expressions for psi. So psi is equal to, let me write it here once again with another angle, sorry. So psi is equal to, let me take this in. Psi is equal to n, okay, into n actually in terms of n. N is a function of n, right? So we can write like n, h n y, okay, exponential minus y square by 2. Exponential minus y square. This is psi, and this depends upon n. Okay, so let us write as psi 0. So psi 0 is equal to n0. What is n0? We have already calculated what is n0. n0 is equal to, this is n0, beta by pi raised to 1 by 4, right? So let us write beta by pi raised to 1 divided by 4 n0 into h and y, and in our case is h0y. And what is h0y? We have calculated here h0y is equal to 1. Okay, so multiplied by 1 into exponential minus y square by 2, and exponential minus y square by 2 is exponential minus beta x square divided by 2. So psi 0 is equal to, therefore psi 0 is equal to beta by pi raised to 1 divided by 4 exponential minus beta x square divided by 2. That is an exponential expression for psi 0. Beta by pi raised to 1 by 4 exponential minus beta x square divided by 2. And now we can get an expression for psi 1. Okay, psi 1. So psi 1 is equal to n1. What is n1? n1 is equal to 1 divided by root 2. 1 divided by root 2. The beta by pi raised to 1 by 4. Beta divided by pi raised to 1 divided by 4 into h and y. H and y in this case is h1y. And what is h1y? We have already calculated h1y. h1y is 2 root beta into x. Okay, this value. So let us write 2 root beta into x. 2 root beta into x into exponential minus y exponential minus y square by 2, and instead of that we can write like exponential minus beta x square by 2. So exponential minus beta x square divided by 2. So this value actually is, we can simplify this like this. Root 2 and 2 are here. 2 is root 2 into root 2. So we can write it like root 2. So this root 2 and 2, they will be cut, and then we will get a root 2 in the denominator. So root 2 into beta by pi raised to 1 by 4 into root beta x, root beta into x exponential minus beta x square divided by 2. You can simplify this further, but that is not necessary. Okay, so that is the expression for psi 1. And psi 2 is equal to and that is n2. N2 is, what is n2? 1 divided by root 8. 1 divided by root 8 into beta by pi raised to 1 by 4. Beta by pi raised to 1 by 4, that is n2, into h2y. h2y is equal to 4 beta x square minus 2. 4 beta x square minus 2 into exponential minus beta x square by 2. By 2. Okay, so that is the expression for psi 2. So now we have different expression for the wave functions: psi 1, psi 0, psi 1, psi 2, etc. Okay, so this is how we are getting the complete solution for the Schrodinger wave equation. And now what is remaining is the energy. Okay, so let me check what is the time. Okay, we can continue. Now we have the expression for psi, the complete solution, complete expression for psi. Okay, and now we are going for energy. And the energy expression can be obtained from our previous equations for alpha and beta. Okay, we have the expressions for alpha and beta here. Alpha is equal to 8 pi square me by h square, and beta is equal to 4 pi square m nu by h. And from this one we can get the expression for E. So let me write alpha divided by beta, that is equal to 8 pi square me by h square, 8 pi square m e by h square, that is alpha, divided by beta. Beta is equal to 4 pi square m nu divided by h, right? So we can write it like 8 pi square m e divided by h square into the reciprocal of this one, that is h divided by 4 pi square m nu. Okay, so that is equal to, so what are the terms that we can cancel? So 8 and 4 are cancelled, then we get 2 here, and pi square and pi square are cancelled, h square, h are cancelled, and we get h in the denominator, m and m are cancelled. Okay, so what is remaining after that? Remaining is 2e divided by h. So that is equal to 2e divided by h. Okay, 2e divided by h. So alpha by beta is equal to 2e divided by h. So 2e by h nu, and we already know that alpha by beta is equal to 2n plus 1. Okay, you can refer our previous lecture. There we showed that alpha by beta is equal to 2n plus 1. Okay, so it means that 2n plus 1 is equal to 2n plus 1 is equal to 2e divided by h, and from this one E is equal to, what is E? 2n plus 1 into h divided by okay, we have a nu here also. Sorry, I forgot to put this nu here. H nu, 2e divided by h nu. So 2e divided by h nu. So the expression for E is 2n plus 1 into h nu divided by 2, right? 2. So we can write it like E is equal to En plus half into h nu. Okay, this is expression for energy, n plus half into h nu. And we already know that here n is equal to 0, 1, 2, 3, etc. So when we get different values of n here, the different possible values of n here, we will get the corresponding E values. So since it depends upon E, let me write it as En. So En is equal to n plus half into h nu. And this En is the vibrational energy, that is the total energy of the harmonic oscillator. And this total energy of the harmonic oscillator depends upon the quantum number n. Okay, so it means that the energies are quantized. Okay, so what are the possible energies when n is equal to 0? When n is equal to 0, then E0 is equal to n plus half into h nu, that is 0 plus half into h nu, or half h nu. Okay, that is the minimum possible energy, half h nu. And this half h nu is the minimum possible energy, means that it always has some amount of energy. So its energy never become equal to 0. Okay, it has some definite value. And so this is called a 0 point energy. This is called 0 point 0 point energy. But it means that you cannot bring this system at an energy level below half h nu. You cannot bring the system at an energy level below half h nu. But what was the classical mechanical picture? Classical mechanical picture. We already saw in the first video that we have an energy profile like this. Okay, and I said that out of this energy profile, the system can take any value of energy. The system's energy can be here, or system's energy can be here, 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 somewhere in between, anywhere. It is like a continuum. Okay, the system's energy can be anywhere here. So if the system is taking an energy here, it means that the energy can come to 0. It means that the oscillator is at a rest. The energy is 0 means the oscillator is at rest. That is the classical mechanical picture. There was no restriction for energy. Okay, and the oscillator can come to rest also. But this quantum mechanical result shows that this is not possible in the case of a quantum mechanical system, because the E0 or the minimum energy is never 0. It has some definite value above 0, that is a half h nu, and therefore that is called a 0 point energy. 0 point energy means that doesn't mean that energy is 0. 0 point energy only means that even at absolute 0, okay, whatever you are doing to reduce the energy of the system, that at that time also system will have some amount of energy which is greater than 0. That is the 0 point energy. Okay, so here the 0 point energy is a half h nu, and that is the lowest value of energy. And now we can calculate the other values, that is for n is equal to 1, then E1 is equal to 1 plus half into h nu, that is 1 plus half. 1 plus half is equal to 3 by 2, or we can write like 1 half h nu. And for n is equal to 2, then E2 is equal to 2 plus half, means 2 half, 2 and half h nu. And for n is equal to 3, then E3 is equal to 3 and half h nu, etc. Okay, so now we can see that each energy level are equally spaced. The lowest energy level is half h nu. The next higher energy level is h nu greater than the lowest one, that is 1 and half h nu. The next higher energy level is again h nu, 1 h nu greater than the E1, okay, that is 2 and half h nu, then 3 and half h nu. So the difference between any successive state, that is delta E is equal to h nu. Difference between any successive energy state is h nu. Okay, so if we are plotting the energy levels here, we can plot like this. So here is one energy level, and this energy level corresponds to n is equal to 0, and then we have another energy level here that corresponds to n is equal to 1, then we have another energy level corresponding to n is equal to 2, then another one corresponding to n is equal to 4, like that. Okay, so this one corresponds to n is equal to 0, this one corresponds to n is equal to 1, n is equal to 2, n is equal to 3. Okay, so the energy levels are E0, here E0 is equal to half h nu, and this is E1, which is equal to 1 and half h nu, and this is E2, which is equal to 2.5 h nu, and this is E3, which is equal to 3.5 h nu. So what is the difference between these? Okay, the difference between this one and this one, that is, what is this difference? 1.5 h nu minus half h nu, that is equal to h nu. And what is the difference between these two states? That is, n is equal to 1 and n is equal to 2 states. That is 2.5 h nu minus 1.5 h nu. That is again h nu. And here also the difference is h nu. It means that all energy levels are equally spaced. Okay, all energy levels are equally spaced. And that is what we have to understand about the energy of the harmonic oscillator. So here the main point is that it has a 0-point energy, means that the vibration can never cease, or vibration can never stop. Always it is under vibration. The quantum mechanical particle is always under the vibration. It will never cease. Even if you are bringing that system to absolute zero, that will continue its vibration with an energy half h nu. Okay, so that is what we can understand from here, and this is in contrast with the classical mechanical understanding. Okay, and now we are going for the plots of psi and psi square. The plots of psi and psi square. Plots of psi and psi square. Okay, so we already have the expressions for psi, and we already know that psi has two parts. Psi has two parts. What are those two parts? The one part is exponential minus beta x square divided by 2. That is one part. And another part of psi, okay, that part is hny, or we can write like hn root beta x. Instead of y, we can write root beta x. Okay, and you know that this exponential minus beta x square by 2, this is a symmetric function. Why it is symmetric? Because we have a x square here. When do you call a function symmetric? For example, when you are plotting this function with respect to x, for negative values of x and positive value of x, if you have the function in the negative side as a mirror image of the function in the positive side, then you can call this as a symmetric function. For example, suppose this is your axis, this is x is equal to 0, and this is plus x direction, and this is minus x direction. And suppose that you have a function like this, okay, function like this, and this is the plot of the function in the minus x direction, and this is the plot in the plus x direction. That is the left hand side and right hand side of this middle axis. Okay, and if we are placing a mirror here, actually the left hand side of this curve is a mirror image of the right hand side, and vice versa. So we can say that this is a symmetric function. This is a symmetric function. Okay, and here also we can see that whatever value you are giving to x, whether it is minus x value or plus x value, that doesn't matter, because we have x square here. അപ്പോൾ നിങ്ങൾ മൈനസ് എക്സ് കൊടുത്താലും പ്ലസ് എക്സ് കൊടുത്താലും നിങ്ങൾക്ക് ഒരേപോലെയുള്ള വാല്യൂ ആണ് കിട്ടുന്നത്. അതുകൊണ്ട് നിങ്ങളുടെ ഫംഗ്ഷൻ അപ്പുറവും ഇപ്പുറവും അല്ലേ, ഈ എക്സ് ഇസിക്കൽ ടു സീറോയുടെ ലെഫ്റ്റിലും റൈറ്റിലും നിങ്ങളുടെ ഫംഗ്ഷൻ ഒരേപോലെ ആയിരിക്കും. കാരണം അതിന് മൈനസ് സൈനെയോ പ്ലസ് സൈനെയോ അത് ബാധിക്കുന്നില്ല, കാരണം അത് എക്സ് സ്ക്വയർ ആണ്. സോ ദിസ് ഈസ് എ symmetric function. Okay, this is a symmetric function. And what about the other part, that is hn root beta x? We know that for n is equal to 0, hn root beta x is equal to 1. Okay, this function is equal to 1. And for n is equal to 1, this function was hn root beta x, that is 2 into root beta x, right? 2 root beta into x. We have already calculated this one. And for n is equal to 2, this is 4 beta x square minus 2. Okay, 4 beta x square minus 2. Okay, Now you look at these functions. 1 means it is just a constant, so that is symmetric. Okay, this is symmetric, that is independent of x, so obviously it is symmetric. It is not going to affect the symmetry of the entire function. That is what is meaning by saying symmetric. And what about this one? That depends upon x. And so for plus x and minus x values, you will get a different values for this expression. So this function is antisymmetric. This is antisymmetric. And what about this one? Here x is it's in the form of x square. Since it is x square, then it is again symmetric. Okay. So what we can understand from this one, this part of the psi is not going to affect the symmetry because it is already symmetric. And the factor which is going to affect the symmetry of the function is this part, that is the Hermite polynomial part. And if for n is equal to 0 and n is equal to 2, they are symmetric. And n is equal to 1 and n is equal to 3, n is equal to 5, etc., it will be anti-symmetric. Okay. So we can write like psi 0 will be symmetric function because this function and this function both are symmetric for psi 0. So psi 0 is symmetric. And like that psi 2 will be symmetric because this function is symmetric and this function is also symmetric. Psi 2 is symmetric. Like that psi 4, etc., they all will be symmetric functions. Okay. And what about the even size, that is not even, the odd size, that is psi 1, psi 3, psi 5, etc., the odd ones. And these you can see that for n is equal to 1, then that is antisymmetric. So psi 1 will be antisymmetric, psi 3 will be antisymmetric, psi 5 will be antisymmetric. Okay. So all these will be antisymmetric functions. Antisymmetric functions. Okay. So all these are antisymmetric functions. So when we are plotting these psi, then we have to take care of this one. When we are plotting psi 0, psi 2, psi 4, etc., we will get symmetric plots. And when we are plotting psi 1, psi 3, psi 5, etc., we will get anti-symmetric plots. So let us see how the plots will appear. Okay, I will show you how the plot will appear. So I have the vertical axis here. This is the vertical axis. And then I have a horizontal axis also. And in the horizontal axis, the x is changing. Okay, it means that this is x is equal to 0, and this is the plus x direction, and this is minus x direction. Okay, minus x and plus x directions. And I am going to plot psi 0, psi 1, psi 2, psi 3, etc. Okay, so let me put the energy profile here, what we are getting from the classical mechanics, just to interpret certain important results. Okay, so I am going to put the energy profile here. Let me take another color. So if you have missed my first lecture in this series, I strongly recommend you to go to that first lecture, means the first lecture of the simple harmonic oscillator, that is a classical mechanical treatment of the simple harmonic oscillator, and I recommend you to go to that. Okay, then you will understand what I am drawing at this moment. So this parabola actually represents the energy profile of the classical system. Okay, so this parabola, and we already know that our system has some discrete energies or quantized energies, right? Quantized energy. Let me draw those quantized energies also here. Quantized energies. So this is E0 state, means state corresponding to n is equal to 0, and this is the state corresponding to n is equal to 1. So let me put here, okay, is equal to 0, and then put another one here, and let me put another one here, and another one here. Okay, so this corresponds to n is equal to 0, n is equal to 1, n is equal to 2, and n is equal to 3, etc. And now what I am going to do is I am going to plot psi functions in this graph. Okay, so when I am plotting the psi functions for the first state, that is psi 0, okay, the plot of the psi 0 will be like this. So this will be the plot of the psi 0. Okay, my drawing is not very nice. You can just suppose that this is very smooth here. Okay, I cannot do more than that. Okay, so this is psi 0, say psi 0, and now I am going to plot a psi 1, and you can see that psi 0 is symmetric one. See, whatever is in the left side of this vertical axis is the mirror image in the right side. Okay, so psi 0 is a symmetric function. Now I am going for the psi 1. Psi 1 is antisymmetric function, right? So the psi 1 will appear like this. It will be like this. Okay, I could have drawn better, but my skill is not that good to draw it better. Okay, let me try once again. Okay, like this. This is a plot of psi 1. And now I am going for the plot of psi 2. Okay, psi 2 plot. So let me mark some points here that I have to go through. So this is going to be psi 2, and you know that psi 2 will be a symmetric function, right? So it is like this. Psi 2. And I'm not so lucky to draw in a better way. My drawing skill is not very good. Okay. If I am using dotted lines, then it will be better. Then I will get a better control. Here the problem is that I don't have so much control over this tablet pen. here. Okay, it will be like this. So this is also a symmetry function. You can see that the left hand side and right hand side are mirror images to each other, and that is psi 2, psi 2. And if I am going for psi 3, again I will get an antisymmetric function. The psi 3 will be like this. Okay, it will be like this. Okay, my drawing is not appearing very nice. I know that. You may be frustrated perhaps after seeing this, but I hope that you understood how it appears. Okay, and now I am going to interpret these things. So when I'm interpreting this one, okay, the last one that I drew was psi 3, psi 3. Okay, so I have psi 0 as a symmetric function here, and here this is a ground state function. This function has no node. Okay, it has no node, ground state function, and this function psi 0 corresponds to E0, that is half its nu, and in that state it has no node. Okay, means the node means zero possibility position or zero probability position, and no such positions can be seen in the first state. Means that if you are looking at any point, any permissible point for this particle, in all those points there will be at least some probability to find the particle. Okay, that is what is meant by saying there is no node. Okay, and but when we are going to the next higher state, that is psi 1 state, then it has a node here. See, it has a node. It meets the horizontal axis. This is where the psi has no value. Okay, the psi has zero value. So it has a node here. Here it has negative value. Here it has positive value, and it is a antisymmetric function. And there is one node. And when we are uh, going for the psi 2, then we can see that it has uh, two nodes. One node is here and another node is here. Okay, and when we are going for psi 3, it has three nodes like this. Okay, so psi 0 has no node, and each additional state has states get some additional nodes, one additional node, right? So um, the ground state has no node. The successive states get one additional node. That is what we can understand from this one. Okay, and another important thing that you can understand from here, if you are looking at these plots, you can see that actually this line, this dotted line, is the turning points of the classical mechanical system, right? So that is a potential barrier of the classical mechanical system. So if we are treating this particle as a classical mechanical, treating this particle classical mechanically, the particle must come here. If the energy level is here, the particle should come here, and then it go back. And when it comes to here, it should meet here, and then it go back. So these are the two extreme positions or turning points. These are the turning points. Okay, I have explained this in the first video. So, but if you are looking at the psi 0 value here, you can see that even after the turning points, you can find some value for psi 0. See, psi 0 values are extending to here, crossing this potential barrier, the classical mechanical potential barrier or classical potential barrier. Okay, So in other words, we can say that the psi function penetrates the potential barrier. Okay, so that is very important result. So that is in contrast to the classical mechanical picture, and the quantum mechanical particle penetrates the potential barrier, and there is some probability to find out the particle even after the potential barrier set by the classical mechanical treatment. Okay, that is what we can understand from this one, and that is true for every state. You can see that for every state there is some penetration, some amount of penetration after the potential barrier. Okay, and if we are going for the plots of psi square, then we can plot psi square like this. See, this is the vertical axis, and here I have the horizontal axis. And if I am plotting psi square, okay, here I have this one for psi 0, so this one for psi 1, and this one for psi 2, this one for psi 3. So if I am plotting psi 0, what I am getting for psi 0 square? So this is the plot of psi 0 square. So let me use the dotted line so that I will get a better control. This is the plot of psi 0 square. Okay, and if I am going for the, let me draw the potential barrier also here. Okay, so here I have the plot of psi 0 square. Okay, psi 0 square. And if I am going for psi 1 square, then the plot will be like this. See, psi 1 you already know that is an antisymmetric function. It has in the left side its value is negative, but in the right side its value is positive. But when we are taking the square, that doesn't mean whether it is positive or negative, because square will be always positive. So the square of this function will go in the upside, right, the positive side. So we will get one um, 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 one part of the psi square here and the other part of the psi square here. Okay, so the psi 1 square will appear like this. Okay, and this is a node. Okay, this is psi 1 square, and if I am going for psi 2 square, the psi 2 square will be like this. Then in the case of psi 2 square, I have a node here and another node here. Okay, so I get something like this one, then go like this one, go like this one. So this is not very nice what I have done here. Okay, like this, and that is psi 2 square. So there is a node and there is another node, and when I am going for psi 3 square, its plot will be like this. So in the case of psi 3, I have 3 nodes. One node is here and another node is here, yes, and here, and another node is here. Okay, so I have okay. So you should be careful about the shape of this curve. Some textbooks draw it like just all these curves with the same height. That is not correct. You can see that when I was drawing the psi here, I was taking some care to draw like that. Okay, actually here this one has the height of this one is greater than the height of the negative height of this one. Okay, so that when you are coming to the extremes, the psi square values in the extremes will be greater than the psi square values in the midpoints when we are going to the excited state. But that is not true in the ground state. If you are checking the ground state, that is very important result. If you are checking the ground state, you can see that the maximum value of the psi square is in the x is equal to 0 position, or x is equal to 0 position is the equilibrium position. So the maximum probability to find the particle is in the middle of or the midpoint or the equilibrium position. But you can see what is the case in the classical mechanical picture. If you are looking at the pendulum of the clock, where you can see the pendulum for most of the time, where you can see the pendulum is moving in this way, right? It comes to rest here, then it moves fast to here. Its kinetic energy is maximum when it reaches here. Then its kinetic energy decreases and comes to rest here, right? Then it is again coming back with an increased kinetic energy, passes this point with a maximum kinetic energy, and then it comes to rest here. So whenever this pendulum is passing this point, it is passing with the maximum speed, right? So it means that the pendulum is not spending too much time in the midpoint. അല്ലേ? അപ്പോൾ വളരെ ഫാസ്റ്റായിട്ടാണ് ഈ മിഡ് പോയിന്റിലൂടെ അത് പോകുന്നത്. അതുകൊണ്ട് മിഡ് പോയിന്റിൽ അത് വളരെ കുറച്ച് സമയം മാത്രമേ ചിലവഴിക്കത്തുള്ളൂ. പക്ഷേ അതിൻ്റെ കൂടുതൽ ടൈം എവിടെയായിരിക്കും അത് സ്പെൻഡ് ചെയ്യുന്നത്? എക്സ്ട്രീം പൊസിഷൻസിലാണ്. കാരണം എക്സ്ട്രീം പൊസിഷൻസിൽ അത് റെസ്റ്റിലേക്ക് വരും. റെസ്റ്റിൽ വന്നതിന് ശേഷമാണ് എക്സ്ട്രീം പൊസിഷനിൽ നിന്ന് അത് തിരിച്ചു വരുന്നത്, അല്ലേ? അതായത് എക്സ്ട്രീം പൊസിഷനിലേക്ക് പെൻഡുലം അടുക്കുമ്പോഴത്തേനും അതിൻ്റെ സ്പീഡ് കുറയും. സ്പീഡ് കുറഞ്ഞെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ആ ഏരിയയിൽ അത് കൂടുതൽ നേരം റിസൈഡ് ചെയ്യും, അല്ലേ? അപ്പോൾ നമ്മൾ തന്നെ നോക്കിക്കഴിഞ്ഞാൽ വെൻ വി ആർ ഇഫ് വി ആർ ഗോയിങ് ഫ്രം വൺ പ്ലേസ് ടു അനദർ പ്ലേസ്, അല്ലേ? നമ്മൾ ഫോർ എക്സാമ്പിൾ ഐ എം ട്രാവലിംഗ് ഫ്രം ചെങ്ങന്നൂർ ടു തിരുവല്ല, അല്ലേ? ചെങ്ങന്നൂരിന് അല്ലെങ്കിൽ അടൂർ ടു തിരുവല്ല, പന്തളം to I am talking about all these things. I am going from Pandalam to Tiruvalla. Let us fix from Pandalam to Tiruvalla. Okay, so Chengannur is in the middle. So Chengannur is the midpoint. So when I am going through here, ഞാൻ തുടക്കത്തിൽ വളരെ സ്പീഡിലാണ് നമ്മുടെ പന്തളത്ത് നിന്ന് തുടങ്ങിയത്. കാരണം എനിക്ക് നല്ല എനർജി ഉണ്ടായിരുന്നു. ഞാൻ ഒരു ബിരിയാണിക്ക് കഴിച്ചിട്ടാണ് നടത്താൻ തുടങ്ങിയത്. അത് സ്പീഡിൽ ഞാൻ ഓടുകയാണ്. അപ്പം ഞാൻ ചെങ്ങന്നൂരൊക്കെ വന്നപ്പോഴത്തേന് എന്ത് ചെയ്തു? എൻ്റെ സ്പീഡ് പകുതിയായിട്ട് കുറഞ്ഞു, അല്ലേ? അതിനുശേഷം ഞാനങ്ങ് തിരുവല്ല അടുക്കാറായപ്പോഴത്തേന് എൻ്റെ സ്പീഡ് എന്ത് ചെയ്തു? വളരെ കുറഞ്ഞ് ഞാൻ വളരെ പതിയെ നടക്കാൻ തുടങ്ങി, ഏന്തി നടക്കാൻ തുടങ്ങി. അപ്പോൾ എന്നെ ഈ കാത്തു നിൽക്കുന്ന കുറേ ആളുകൾ ഇവിടെ എല്ലാം ഉണ്ട്. ഞാൻ വളരെ പ്രശസ്തനാണെന്ന് നിങ്ങൾ വെറുതെ കരുതിക്കോളൂ. അങ്ങനെ എന്നെ കാത്തു നിൽക്കുന്ന, ഞാൻ ഈ ഓടിപ്പോകുന്ന അല്ലെങ്കിൽ കാണാൻ കുറേ ആളുകൾ വഴിയിലെല്ലാം നിൽക്കുന്നുണ്ട്. എവിടെയുള്ള ആളുകൾക്കായിരിക്കും എന്നെ ഏറ്റവും കൂടുതൽ കാണാൻ കഴിയുക? ഞാൻ തുടക്കത്തിൽ പന്തളത്തു നിന്ന് ഓടിയപ്പോൾ ഭയങ്കര സ്പീഡിനാണ് പോയത്. അപ്പോൾ അവരൊക്കെ നോക്കിയപ്പോൾ എന്തോ മിന്നൽ പോലെ അങ്ങ് പോയതേ കണ്ടുള്ളൂ. കാരണം ഞാൻ വളരെ സ്പീഡിലായിരുന്നു. ഞാൻ ഒരുപാട് ടൈം ഓരോരുത്തരുടെയും അടുത്ത് ഞാൻ ഒരുപാട് ടൈം അവിടെ സ്പെൻഡ് ചെയ്യുന്നില്ല. കാരണം മിന്നൽ പിണർ പോലെ അങ്ങ് പോകുമായിരുന്നു, അല്ലേ? ചെങ്ങന്നൂരൊക്കെ ആയപ്പോഴത്തേനും ആളുകൾക്ക് കുറച്ചും കൂടെ ഒക്കെ കാണാനുള്ള അവസരം കിട്ടി. കാരണം എൻ്റെ സ്പീഡ് കുറഞ്ഞു. അപ്പോൾ എൻ്റെ മുഖമൊക്കെ അവർക്ക് നന്നായിട്ട് കാണാൻ പറ്റി. പക്ഷേ ഇവിടുന്ന് അങ്ങ് തിരുവല്ലയെ അടുപ്പിച്ച് ആവാറായപ്പോഴത്തേന് അവിടേക്കുള്ള ആളുകൾക്ക് നോക്കിയപ്പോൾ എന്നെ കുറേ നേരം അവർക്ക് കാണാൻ പറ്റി. കാരണം അവിടേക്ക് ആയപ്പോഴത്തേന് ഞാൻ വളരെയധികം കഷ്ടപ്പെട്ട് നടക്കുകയാണ് ചെയ്യുന്നത്. അവർക്ക് എന്നെ കുറേ നേരം കാണാൻ പറ്റി. അപ്പോൾ എവിടെയാണോ എൻ്റെ സ്പീഡ് കുറയുന്നത് അവിടെയായിരിക്കും ഞാൻ കൂടുതൽ നേരവും സ്പെൻഡ് ചെയ്യുന്നത്, അല്ലേ? അവിടെയാണ് എന്നെ കാണാൻ കൂടുതൽ സാധ്യതയുള്ള മേഖല എന്നർത്ഥം, അല്ലേ? കൂടുതൽ സമയവും സ്പെൻഡ് ചെയ്യുന്നത് അവിടെയായിരിക്കും. പക്ഷേ ഇവിടുത്തെ ഹാർമോണിക് ഓസിലേറ്ററും അതുപോലെയാണ്. ഹാർമോണിക് ഓസിലേറ്റർ ക്ലാസിക്കലായിട്ടുള്ളൊരു ഹാർമോണിക് ഓസിലേറ്റർ കൂടുതൽ സമയം സ്പെൻഡ് ചെയ്യുന്നത് അതിൻ്റെ എക്സ്ട്രീം പൊസിഷൻസിലായിരിക്കും. എന്ന് പറഞ്ഞാൽ പ്രോബബിലിറ്റി ടു ഫൈൻഡ് ദ ഓസിലേറ്റർ will be maximum at the extreme position and will be minimum at the mid position, അല്ലേ? അപ്പോൾ നമുക്ക് പെൻഡുലത്തെ ഒരു നോക്ക് കൺകുളിർക്ക് കാണണമെന്നുണ്ടെങ്കിൽ നമ്മൾ എവിടെ പോയി നിൽക്കണം? അതിൻ്റെ എക്സ്ട്രീം പൊസിഷനിൽ പോയി നിന്നാൽ മതി, അവിടെയാണ് അത് കൂടുതൽ ടൈം സ്പെൻഡ് ചെയ്യുന്നത്. പക്ഷേ ഇവിടെ അങ്ങനെയല്ലത് കാണുന്നത്. ഇവിടുത്തെ ക്വാണ്ടം മെക്കാനിക്കൽ റിസൾട്ട് അനുസരിച്ച് വെൻ ഇറ്റ് ഈസ് ഇൻ ദ ഗ്രൗണ്ട് സ്റ്റേറ്റ് അല്ലേ, ഈ സിസ്റ്റം ഗ്രൗണ്ട് സ്റ്റേറ്റിലിരിക്കുമ്പോൾ ഇറ്റ് സ്പെൻഡ്സ് മോസ്റ്റ് ഓഫ് ഇറ്റ്സ് ടൈം അറ്റ് ദ മിഡ് പോയിന്റ്. അതുകൊണ്ടാണ് ഇവിടെ പ്രോബബിലിറ്റി ഏറ്റവും കൂടുതൽ. പ്രോബബിലിറ്റി ടു ഫൈൻഡ് ദ പാർട്ടിക്കിൾ ഇൻ ദ മിഡ് പോയിന്റ് ഈസ് ഹയസ്റ്റ്, റൈറ്റ്? So the particle spends most of its time in the midpoint. This is in contrast to the classical mechanical result. So this is very interesting. ക്വാണ്ടം മെക്കാനിക്സിലേക്ക് വരുമ്പോൾ നമുക്ക് ക്ലാസിക്കൽ മെക്കാനിക്സിൽ കാണുന്നതിൻ്റെ നേരെ വിപരീതമായിട്ടുള്ള ഒരു ഫിനോമിനനാണ് ക്വാണ്ടം മെക്കാനിക്സിലെ പാർട്ടിക്കിളിൻ്റെ ഗ്രൗണ്ട് സ്റ്റേറ്റിൽ ഉണ്ടാകുന്നത്. ദ പാർട്ടിക്കിൾ വിൽ സ്പെൻഡ് മോസ്റ്റ് ഓഫ് ഇറ്റ്സ് ടൈം ഇൻ ദ മിഡിൽ പോയിന്റ് ഓർ മിഡ് പോയിന്റ് ഓർ ഇൻ ദ ഇക്വിലിബ്രിയം പോയിന്റ്. ഓക്കെ, സോ ദാറ്റ് ഈസ് വെരി ഇൻട്രസ്റ്റിംഗ് ഫൈൻഡിങ്. ഇനി നമ്മൾ എനർജി കൂടിയ സ്റ്റേറ്റിലേക്ക് പോകും തോറും നിങ്ങൾക്ക് കാണാൻ ഒക്കും, ഞാനിവിടെ വരച്ചിരിക്കുന്നത് വളരെ ആലോചിച്ച് തന്നെയാണ് വരച്ചിരിക്കുന്നത്. ഈ ഫങ്ഷൻസ് എങ്ങനെയാണ് പ്ലോട്ട് ചെയ്യപ്പെടുന്നത് നിങ്ങൾക്ക് കാണാം. നമ്മൾ ഹയർ എനർജി സ്റ്റേറ്റിലേക്ക് പോകും തോറും നമുക്ക് ഈ എക്സ്ട്രീമിൽ വരുന്ന പീക്കുകൾ കണ്ടോ, പ്രോബബിലിറ്റിയുടെ എക്സ്ട്രീമിൽ വരുന്ന പീക്കുകളുടെ ഹൈറ്റ് വളരെ കൂടുതലാണ്. എക്സ്ട്രീമിൽ വരുന്ന പീക്കുകളുടെ ഹൈറ്റ് കൂടുതൽ, ഇവിടെ നടുക്കൊക്കെ വരുന്ന പീക്കുകളുടെ ഹൈറ്റ് വളരെ കുറവാണ്. എന്ന് പറഞ്ഞാൽ അതിൻ്റെ അർത്ഥം എന്താണ്? വെൻ വി ആർ ഗോയിങ് ടു ദ എക്സ്ട്രീം ടു ദ എക്സൈറ്റഡ് സ്റ്റേറ്റ്സ്, കൂടുതൽ എക്സൈറ്റഡ് സ്റ്റേറ്റിലേക്ക് പോകും തോറും ഈ പാർട്ടിക്കിൾ എന്ത് ചെയ്യും? അതിൻ്റെ എക്സ്ട്രീം പൊസിഷനിലേക്ക് വരാനുള്ള സാധ്യത കൂടുകയാണ്, അല്ലെങ്കിൽ ക്ലാസിക്കൽ മെക്കാനിക്കൽ പിക്ചറിനോട് അത് കൂടുതൽ അടുക്കുകയാണ്. ഓക്കെ, അത് മിഡ് പോയിന്റ് കൂടുതൽ ടൈം സ്പെൻഡ് ചെയ്യത്തില്ല, പകരം അത് കൂടുതൽ ടൈം സ്പെൻഡ് ചെയ്യുന്നത് എക്സ്ട്രീം പൊസിഷൻസിലായിരിക്കും എന്നുള്ളതാണ് ഈ റിസൾട്ട് കാണിക്കുന്നത്. സോ ഇറ്റ് അപ്രോച്ചസ് ക്ലാസിക്കൽ മെക്കാനിക്കൽ ബിഹേവിയർ when it is going to the excited states. Okay, that is what we can understand from the Psi square plots. അപ്പോൾ നമ്മൾ വളരെ വിശദമായിട്ട് ഈ ഫംഗ്ഷനെ പറ്റി നമ്മൾ നോക്കുകയുണ്ടായി. നമ്മൾ ഈ വീഡിയോയിൽ നമ്മൾ ചെയ്തത് എന്താണെന്ന് വെച്ച് കഴിഞ്ഞാൽ, we derived the expression for the function, then we plotted the function, then we plotted the square of the functions, and we got some interesting quantum mechanical results. And also we derived the expression for energy, and we plotted the energy as well. And we got some interesting quantum mechanical results. ഇത് വളരെ ലെങ്തി ആയിട്ടുള്ള ഒരു വീഡിയോ ആയിപ്പോയി എന്ന് എനിക്കറിയാം. എന്നെങ്കിലും നിങ്ങൾ ഇത്ര നേരം കണ്ടിരുന്നു എന്നുള്ളത് വളരെ ഭാഗ്യമാണ്. I hope you benefited from this one. Okay, and if you benefited from this, let me know. Okay, and if you have any doubt, please comment here, or you can call me directly, or you can text me, or you can send me a message in the WhatsApp, or in whichever way you like. Okay, so thank you for watching. This is the end lecture of this portion. This is the last lecture of this portion. I hope you reached here from the first of this series. Okay, നിങ്ങൾ അപ്പോൾ എല്ലാ വീഡിയോസും കാണാൻ ശ്രമിക്കുക, ആദ്യം മുതൽ അവസാനം വരെ കാണാൻ ശ്രമിക്കുക. അപ്പോൾ ഇത്രയും കാണുമ്പോൾ നിങ്ങൾക്ക് ക്വാണ്ടം മെക്കാനിക്സിൽ ഒരു നല്ല ബേസിക്സ് ഉണ്ടായി എന്ന് ഞാൻ വിശ്വസിക്കുകയാണ്. And let me know whether you benefited from this one. You can comment here whether you benefited from this lecture series. Okay, and thank you for watching, and stay tuned.